Hello, this is Raed. I'm an assistant professor at the University of Michigan, and I'll be talking about multi-agent collaborative Bayesian optimization via consensus. Fundamentally, I'm talking about how to do collaborative trial and error. So let me start by describing Bayesian optimization. Bayesian optimization is a way to do black box optimization. It stems from Bayesian decision theory, and the goal is to optimize a black box function. And really, from an engineering perspective, optimizing a black box function implies trial and error. Okay, so to give an example here, let's assume there is a chef, and the chef is trying to bake a cake. That he is trying to find the best amount of sugar to get the best taste possible. How does a chef do that? By trial and error. An experiment, you bake a cake with a specific sugar level, you taste, and then you decide on the next experiment to do. And the hope is to get the best taste and find the optimal sugar level with the fewest experiments possible. This is what trial and error is about. And fundamentally, Bayesian optimization is a decision-making problem because our goal is to decide on the next experiment to do in hope we get the optimal solution with the fewest experiments possible. So today I'll be taking Bayesian optimization to a collaborative level. In the sense, let's assume there are multiple chefs and they want to collaboratively learn from each other to get the sugar level faster than doing things individually. How can we do that? I will also tackle the situation of what if the chefs have different palates? Some like sugar more than others. How can we collaborate under heterogeneity? This is the end goal of this talk. Okay. So let me go back and also introduce Bayesian optimization slightly mathematically. So remember, the goal of Bayesian optimization is to optimize a black box function f. We have a function we do not know. It's an expensive function to evaluate every time we need to do an experiment. So how does Bayesian optimization proceed? The first step in Bayesian optimization, you gather a few data points. You bake the cake with different sugar levels, okay? And then you build what we call a posterior belief. And really, this posterior belief is where the word Bayesian came in, okay? So based on the few observations that you have, you build a posterior belief. This is the probability of f given d, the data that you have. And really what you need from this posterior belief is two things. The mean, the predictive mean. So for any x, for any sugar level, you should be able to estimate or predict a predictive mean, and the variance. The variance is very important in any posterior belief in Bayesian optimization because fundamentally, getting to the optimal implies the reducing our uncertainty on where the optimal location is. Okay. And then you have the posterior belief, and then what follows the posterior belief is what we call a utility function. The utility function uses the posterior belief, okay, and quantifies the benefit that we do an experiment on any location X, okay? To give you a very simple example, let's assume the utility function for us is simply the upper confidence bound, okay? So it's that line at the top. This is my posterior belief in the posterior belief variance is given in green, in shaded green, and the upper confidence bound is that line above. Okay. So one way to define my utility function is simply the upper confidence bound. Okay. And the upper confidence bound tells me what is the utility, what is the benefit of doing an experiment at any location. And then we maximize our utility. We find the experiment what we choose is one that maximizes our utility, okay? And in this situation, if you can see here, the best experiment to do is this location, okay? And remember, you can always see in these utility functions, if you define the upper confidence bound, we have this trade-off between exploration and exploitation. So exploitation is through the mean, exploration is through looking at the variance. So both will play a role in helping us decide on the next experiment, okay? But really, what was the motivation for our problem? This is just single objective Bayesian optimization. We were working with some collaborators on 3D printing farms, okay? And in 3D printing farms, you have multiple 3D printers. They're located in physical proximity, and they're all printing the same task per se, okay? Interestingly, we found out that if the printers are even slightly beside each other, slightly at different levels, then their optimal process parameters are very different. For example, the optimal speed for a printer on level 1 will be very different from a printer of level 2. Okay. So this is a small example of how small differences in these printers, their location in a room will cause differences in their optimal solutions. But still they have commonalities. Their optimal solutions are not very far away from each other, but just their positioning is causing these differences. This is an example of how the acceleration versus speed will differ across these printers just based on location. So we ask this fundamental question. We have multiple printers. We need them to collaborate, okay? So that we get the process parameters much faster than each one working individually, but we also want to handle heterogeneity. So really our fundamental challenges in this problem are the following. One is how to collaborate. There is not much literature, unfortunately, on collaborative optimal design or Bayesian optimization, okay? The second challenge that we have is how do we collaborate in the presence of heterogeneity? Take this example here, okay? You can see that the black box functions across the different printers have some differences. They still have some commonalities, but doesn't mean the optimal solution for one is optimal exactly for the other, okay? And finally, we ask this question of if we need privacy, how can we collaborate while respecting privacy? Those are the three challenges that we want to tackle. Just to give you a snapshot of the literature, there is a lot of literature on what is called batch Bayesian optimization. Batch Bayesian optimization is simply defined for parallelization. So you have one black box function, and your goal is instead of doing a single experiment, you want to do multiple experiments. Okay, but remember our key difference is here we may have heterogeneity across the different black box functions. So batch Bayesian optimization doesn't work because you cannot fit one surrogate model for everyone. Even if the data points are slightly shifted, one surrogate will not fit everyone. And then you have recent literature on what is called federated Bayesian optimization. Federated Bayesian optimization also still assumes there is homogeneity, and the goal there is just privacy. Our hope is collaboration in the presence of heterogeneity. And this is the key distinction from what exists in the literature. Okay. So let me set notation a little bit. Let's assume that we have a data set at time 0. We collected some data points. We baked the cake at some sugar levels. Okay. And our goal is at any time t to decide on the new experiment we want to do. This is our goal. We want to decide on the next experiment we want to do. And in Bayesian decision theory terminology, the consequence of our experiment, the reward, is basically the taste. Okay, so you run an experiment and you observe a consequence, you observe a reward. And this reward can be noisy. Okay, you can have some Gaussian additive noise that is observed. Okay, and then here then you have your data, you also have your utility function that we defined previously. Your utility function simply quantifies the benefits of doing an experiment at any x. Okay, but remember that I do not know the output for any x, so I cannot calculate the utility for any x. This is why I need a surrogate. The surrogate will help me estimate this utility function. Okay, so the surrogate is basically a surrogate on my output y. Okay, and it really, you simply substitute your y with your surrogate. Okay, and then what happens in Bayesian optimization or Bayesian decision theory in general is you're trying to find your experiment, your x, your input, that maximizes your utility in expectation. And here we take expectation because our output is random. We do not know it. We have not observed it. Okay. And this is fundamentally the general notation of Bayesian optimization. So then how can we do collaboration? Okay. A first thought that comes to mind is let's assume, first of all, let's assume we have right now K clients. Okay. Let's assume we have K clients. Okay. And all the clients want to collaboratively optimize their own black box function, f of K. There is not one black box function for everyone. And they want to do that by deciding on the next experiment. So we want to collaboratively decide on the next experiment. And here everyone will get their own next experiment. This is our goal. So what is a first thought that comes to mind? What if we follow the notion of collaborative, federated learning in general, which basically says we have multiple clients. Let my decision maximize my expected utility, but in expectation over all my clients. So let me find the solution that maximizes the utility the average utility over all the clients that I have. This is the first thought that comes to mind. But unfortunately, this idea does not work because we have heterogeneity. The expected utility, the average utility, does not make a lot of sense when heterogeneity exists. And specifically here, another challenge here is if we're trying to find one experiment that maximizes the utility, basically we're asking all the clients to do the same experiment. If they have commonalities, that's a lot of redundant effort. So what was our idea? Actually, our idea is very simple. We bring this notion of consensus to optimal sequential design or Bayesian optimization, okay? And consensus will help each client to collaboratively decide on their individualized, personalized next experiment. So let's see our formulation. The formulation is very simple. It's very generic and rather simple. So at the beginning, each client will maximize, every client has their own data, and they will maximize their expected utility. So every client is doing single Bayesian optimization. That's it. But then the result of this local Bayesian optimization, we call it XC for client K. C means a candidate. This is not where the client will do their next experiment. This is just a candidate solution. And then the actual experiment that every client K does is a weighted combination of all the candidate solutions. And this weight is dictated by some consensus matrix W. W basically dictates how much one client's decision will affect the other. Okay. And here W, it's very important to note that W is a doubly stochastic matrix. Because the sum of the columns and the sum of rows is 1. Okay. With non-negative elements. So you can see here, basically, it's a two-step procedure. That's simple. Every client finds their maximizer of their expected utility, but the actual experiment is a weighted combination of all the client's decisions. Okay. Here, just for the sake of time, I will not talk about the relationship with consensus optimization. This is not really consensus optimization, but we got inspired from there. But just to emphasize some fundamental properties, the fundamental properties of this approach, I will talk about how to design W soon, but the fundamental properties is W is a W stochastic matrix. And the key idea is that after doing this consensus operation, every client will get their own experiment. We are not repeating experiments. Let's assume W here is 0.70. We have 2 clients, and W is as such. And let's assume each client 1 says, I think my optimal experiment is 5. The second client says their optimal experiment is 7. Then after consensus, client 1 will do their actual experiment at 5.6. Client 2 will do their actual experiment at 6.4. Okay, so every client gets their own solution. So it's naturally distributed. And more importantly, this operation, the consensus operation, only requires sharing X, the input. And this is our approach for privacy. Instead of sharing the output, for example, you're not sharing you're in a healthcare setting, you're only sharing the dosage that each client took, but not their outcome. Okay, this is our approach to preserve privacy here. And this is the beauty. It only requires to share X. And most importantly, W is a function of time. So this is a general framework where W can be adjusted, can be dynamically changed with time. Okay, basically based on the information gained from others, I can change it. I can change it based on my confidence in my own surrogate. This is a general framework. You can change it in any way possible. Okay, and indeed you can think about W as a weighted combination of permutation matrices. So instead of I give you your solution, you give me my solution, we're taking a weighted combination of these permutation matrices. Okay. So before describing how we design W, I'll give you some examples, but I intentionally want to keep this framework generic. The approach is very simple from a collaborative perspective. Every client will do their experiment here after the consensus operation. They observe the response. They observe the taste of the cake. They have a new data point. They augment their data set, fit the Gaussian process or whatever posterior belief you want, find their local solution, their candidate local solution, send it to a central server or send it to each other. Then we do the consensus operation, we do the actual experiment and repeat it. And the beauty here is collaboration can happen. Every client will send to a central server or they can send to each other and have W. In all cases, you can find your next experiment. So this is consensus is the key idea here. I want to highlight something that I think is very interesting, which is the fact that in our case, in any case where there is heterogeneity, W of T should go to identity. So no matter what, if there is heterogeneity, at some point collaboration should stop. Collaboration should decay. Take a very simple example. Let's assume every client right now is at their optimal solution. Then any W that is not identity will move me away from my optimal. So that means others are hurting me. And really, this is the notion of W, why it should go to identity, because at the early stages, all the clients will guide each other to a near optimal solution, and then eventually everyone should do their own thing. This is why one matrix we propose is simply a matrix where the off-diagonal elements decay linearly. Another, in the paper, we also propose what we call a leader-driven approach, much like meta-heuristics, genetic algorithms. Follow the leader. If someone is doing very well, through some information gain measure, I can follow them more. Okay, but eventually this collaboration should dwindle. Okay, and it turns out that this approach has nice theoretical guarantees. Here, there is a caveat. I will not go into details. Here, we just show that the regret for each client will decay sublinearly. Okay, and that means eventually, asymptotically, every client will find their optimal solution. Okay, but here we have some strong assumptions. Okay, I will not go into the theoretical details, but I want to note that in this currently there is a very fundamental problem in Bayesian optimization, is that we still do not understand the properties of the utility functions. Even if we understand the properties of the Gaussian process, how the generalization error increases, or how well we are estimating the mean, okay, this is actually the decay rate of how well we estimate the mean. We don't know how well we are able to estimate the utility function. So our properties on the surrogate cannot easily translate on the properties of the utility function. So here we put some assumptions that we believe we conjecture to be true, but we could not prove them. And this is actually a big open problem. If solved, will revolutionize Bayesian optimization, is really understanding the properties of the utility. But anyways, I just want to note there are strong theoretical guarantees with some assumptions, regularity assumptions, that I think are a little bit tough here. Okay. But in practice, it works perfectly. I will not go into some experiments we had. Here we show that the power of collaboration, the more collaborators you have, the faster everyone can get their optimal solution. But I want to emphasize in a real life experiment that we did, we actually, we brought this experiment to material science, where we tried to bake a compound by optimizing its components. We were specifically trying to optimize a hydrogel, and the components of the hydrogel will basically alginate, water, some different compounds. And our goal was to optimize what we call the shear storage modulus, okay, through the phase angle. So we have a problem here. It's a material science problem. We're trying to optimize how much each compound, the concentration of each compound, to get the best product possible. And what we did is we brought actually 4 chemists, okay? And we asked the 4 chemists to work individually. And we brought 4 chemists and we asked the 4 chemists to work collaboratively using our consensus algorithm. And at every stage, everyone does one next experiment. So the data from one side is not greater than the other. The only difference is one set of clients is doing consensus. The others, no consensus operation. And we indeed found that through collaboration, the collaborative group can get better solutions much faster. Not only better solutions, but much faster with fewer experiments. So this was our experiment to showcase success. And this paper is available on arXiv. It's called Collaborative Sequential Design via Consensus. And we have another paper along this line that tackles a similar problem, but is adversarial in the sense no matter how heterogeneous the clients are, we can get strong theoretical guarantees. That was just published in Technometrics. It's called Multi-Agent Collaborative Bayesian Optimization via Constrained Gaussian Process. Thank you, everyone.